Thanks everybody for coming to this meeting. This is our fourth technical symposium session, and this is the advanced packaging session for the IMAPS New England chapter. Our general chairs are Dave Solms and Michael Johnson. I'm Matt Bracey. I'm the president of the IMAPS chapter for this year and next year. And I run my own manufacturer's representative firm. And I cover New England, and I specialize in capital equipment. The IMAPS New England chapter is recognized as the largest active chapter of IMAPS. This is our 47th symposium. This one's a little different than the rest, as in it's virtual and not live for obvious reasons. We typically hold our symposiums on a Tuesday in May, and there's normally about 40 technical speakers and 55 exhibitors. And we cover all assets of semiconductor and electronic packaging. And Michael Johnson is a senior principal manufacturing engineer from MACOM, and he has a BS in mechanical engineering from Worcester Polytech, and 21 years with MACOM. And Dave Solms is the founder and principal of DSNA LLC, and it's a technical business development consulting firm. And Dave has operated that for 18 years. He has 42 years of electronics thermal management experience, and is a general chair for 2 annual thermal management technical workshops. And Dave has a Bachelor of Science and an MBA from Clarkson University in Potsdam, New York. And he is a Society Fellow of IMAPS. This is I don't know, Dave, are you taking this from here? Or did I cut you off? You're muted.
Thank you. Thanks for allowing me to unmute myself, Matt. This is a calendar of the recent events we've had for the IMAPS New England chapter going back to last October. What we've been doing is interspersing the chapter regular monthly technical meetings. For this year, what we've done is we've put a symposium technical session in alternating with the chapter meetings. So we've had a chapter meeting in October with Eric Perfecto from IBM Research at the new IBM Research Lab in Albany. Then in November, we had the RF and microwave session. That was the first of 2. In January, we had a chapter technical meeting with a presentation from Fujifilm Electronic Materials. In February, we had the second of the 2 RF and microwave chapters from the symposium as a virtual event. In March, we had a chapter technical meeting with a presenter from DuPont Imaging and Electronics nearby in Marlborough, Massachusetts. So that's the recent events calendar. Oh, tell me again, it's locked up. Oh, please. Why does this happen? There we go. Takes a few minutes to figure out what happens. In terms of logistics, we would like to ask everyone to hold the Q&A until following the presentation for each presenter. There is a Zoom chat box function, and you can write in a question for the speaker. Make sure, please, that you mark it as everyone in terms of the destination and not a private message. That's how we'll handle the input on Q&A. Michael Johnson, as co-chair for the symposium, Michael will be organizing the questions, and then we'll work through those with the speaker. We should have an email going out to you at a later date that will include information about the availability of the presenter's slide sets. This session is being recorded, so we will also have a recording of the entire session. We're expecting that we'll finish today at approximately 12:25 p.m. US Eastern Time. And Matt will have everyone's microphones turned off except for the presenters for the presentations. And our next will be Richard Holman. Richard is the session chair for this advanced packaging session. He's principal process engineer for ASM Next in Billerica, Massachusetts. He completed a PhD in physics from Stanford in 1982. And he has been with NEX and EXX since 2006. He has previous work experience with FEI, Ultratech Stepper, and Digital Equipment Corporation. and long work experience in total in semiconductor processing, packaging, MEMS fabrication, lithography, thin films, ion beam, and electroplating work. He is chairing for this year the IMEP's New England chapter technical meetings program. So I will stop speaking, and Richard, yours.
Thank you, Dave. Can you hear me?
Yes.
Good. Okay. And thank you for that introduction. Unfortunately, our first scheduled speaker, Frank Muscolino, had to withdraw we will move ahead with our other two speakers. We are hoping to include Frank's talk in one of our technical meetings, perhaps sometime in the fall. But we're fortunate to have our two other presentations today. We'll start with Robert Patty. He's the president of Enhanced Semiconductors Incorporated, spearheaded the development and delivery of cutting-edge 3D and 2.5D integration technology, managed hardware engineering teams in several organizations, received the 2009 SEMI Award for his pioneering work in 3D IC integration, and the 2015 3D Insights Individual Achievement Award. And he'll be speaking on 2.5 and 3D integration technology and application. So let's bring on Robert Patty.
Good morning, everyone. And as soon as it lets me share the screen here, I'll pick even the right one. So what I'm going to do this morning is I'm going to walk through the 2.5 and 3D technology. I'm primarily going to be talking about interposers and covalent oxide bonding. Commercially, it's known as DBI. It was pioneered by Ziptronics or Zybond. There are certainly other technologies out there, and we practice a number of them ourselves. But I'll step through some of the motivations and some of the gotchas that we see out there. So I like the cartoon that you see there from Sidney Harris. You know, you do all this neat stuff and then a miracle occurs and you get an answer. A lot of advanced packaging has looked like that historically. If we start with some motivation, you know, this is a well-worn road. I'm sure all of you have seen all the reasons why we're coming to the end of Moore's Law. If you look at it from an economic standpoint, we're done. We were done at about 28 nanometer. The primary cost of building chips, they're the largest single cost, is driven by lithography. And once you start having to do double patterning and E-beam EUV, the costs have been rising. So the cost per transistor has been going up since 28 nanometer. But we can get some more density, and arguably there's different kinds of power savings and other neat things. I'm not here to predict that it's going to grind to a halt, but certainly the air is getting pretty rarefied with $200 and $300 million chip programs. Another thing driving, I'll say, the revolution or evolution of semiconductors into advanced packaging has been the Internet of Things. And really what underlies the Internet of Things and why it drives us this direction is we're doing all this more than more stuff. We have a lot of photonic things. There's many different types of sensors. There's lots of heterogeneous integration. You name it. And actually on this slide, at some point or another, we have built everything on that slide with the exception of the battery. We've never actually had to integrate a battery onto an interposer. But certainly all of those other objects, at this point, we have at some point or another integrated into an advanced package device. And what is advanced packaging? Well, we consider it to be the 2.5 3D assembly of chips. So this is kind of a poster child picture of what we consider it. It could have 3D stacks. It could have copper pillars, micro bumps. It may or may not have an interposer, passive or active. It's really using semiconductor processes to give you packaging output. So if it's something you need to do in a fab, we generally consider that to be advanced packaging. If we stop for a moment and talk about interposers, silicon interposers are still the cheapest alternative. Organic interposers are running about 10 cents a square millimeter, 7 to 10 cents. Silicon interposers are running in the 3 to 5 cent a square millimeter range. And while that sounds bizarre, and if you'd asked me 5 years ago, I would say that the organic packaging folks would never cede this space to the silicon guys, but they have. Silicon folks can use well-depreciated older equipment because we build everything very large. You can see the structures here. A lot of the industry, like the GPUs and the folks at Xilinx who use silicon interposers, are using the last or the top 3 metal layers from a 65 nanometer process. So they're roughly 1 micron geometries. At Enhanced, we build thicker metal interposers because we try to propagate at higher frequencies than they need to. So we tend to use 2 micron line and space with 2.5 micron thick metals. That gives us the ability to go 30 millimeters at 4 gigatransfer. And that, when we originally started it, was kind of the requirement for customers that wanted to put large chunks of memory on interposers with processors. So what are the choices and risks as we look at the different kinds of technology? If you look at the bottom of the slide where you have things like POP, package on package, it's practiced by ASE, Amcor, many of the quintessential well-known packaging folks. It's very low cost, but there's very limited interconnect, and you have a lot of parasitics still left, even though you've brought the chips together. At the opposite end, kind of at the top, you're looking at wafer-to-wafer bonding or monolithic sequential assembly of 3D. Those processes are, in terms of cost per connection, are way, way better. To give you a scale, when we do wafer-to-wafer assembly, we can bond, we do interconnect down to about 2.5 microns commercially. Experimentally, the smallest stuff we've built is 0.8 micron pitch. We can have hundreds of millions of interconnects on a wafer. So it's far, far higher density that than you could do with a POP. Those processes are all fab-like processes. And then there's virtually a continuous spectrum from this very high end to, I'll kindly use the word, the low end advanced packaging of something like POP. So challenges and opportunities. Silicon interposers are great little things, but they are glass. There's fragility, handling. The industry has been using 100 micron thick interposers. Shipping 100 micron wafers around the world is not for the weak of heart. It is, we see a lot of wafer breakage at that thickness. So it really requires effort in working with your supply chain. And typically you have to ship really thin interposers like that on handle wafers. The organic interposers, great stuff, but it's a real cost challenge for the people in those marketplaces, because they don't have clean rooms, they don't have steppers. As they get below the 5, below 5 microns, they start to need to look at real clean rooms and stepper technologies and planarization. It is an enormous hill for them to climb. The other thing with the organic interposers is you can build them really big, but the CTE, coefficient of temperature expansion, mismatches can rip things apart. And an earlier slide, you may have seen building silicon interposers to about 50 by 50 millimeters. You can go a little bit larger. That is limited by the mismatch between the silicon and an organic substrate that you want to attach it to. You get bigger than that, it just simply rips the solder balls off either the organic or the interposer. Something up and coming is, large glass interposers. A lot of people have been dabbling in this. We ourselves use glass interposers made by Mosaic, which are in wafer form. But basically, this is the same technology that is used to build our flat panel, monitors and TVs, which we're all staring at right at the moment. So that technology is promising, but it's not directly applicable. The metals and that they use on these tend to be very high resistance. So it's similar and different, but different. The fundamental underlying technology is there, but work needs to be done if that becomes more commercially required. Probably the biggest underlying challenge and cost challenge is, how do we test this stuff and where do we test this stuff? I spend a lot of time in committees discussing how we do this. What do you test at the foundry? What do you test at packaging? What do you test after it's finished assembly? And it's a cost trade-off. And this requires a very careful analysis. I'll give you a good example of a really hard problem to solve in this regime. We have built commercial detonators in the past for, blasting caps, digital blasting caps. So this is something that gets blown up. It needs to be really, really inexpensive. It has a very tiny die in it that's on the order of a few cents. Testing that die is probably on the order of a nickel, so it exceeds the cost of the silicon. We get a whole bunch of them on a wafer, on the order of 50, 60,000 of them. Die probing all of them would be extremely expensive. And when it's all said and done, there would only be about 100 bad die out of that 50 or 60,000. So in this case, we don't do any test. They do all blind assembly. The package is finished. And before it goes into the final assembly, which is the blasting cap itself, they test it. And it's because that's the best cost trade-off. It is cheaper to test the finished parts because they absolutely need to be tested. It's amazing how excited people get about explosives going off at the wrong time. So it's best to do it on the final thing, and you throw away the 100 or so bad devices that exist out of the 50 to 60,000 we get, because that point you're throwing away about $25 worth of material. And if you were originally testing the wafers, you would add $1,000, $2,000 best case to that wafer. And you still have to go through and do a test later after it's assembled. So, moral of the story in a lot of this advanced packaging: significant planning required, careful analysis of where the yield costs are, You need methodologies. You know, if you have really high pin counts, we're doing, you know, if we're doing wafer to wafer bonding, and we can have 30 million interconnects on a die. I'm not aware of any 30 million channel testers. They don't exist in nature, so you have to have a different strategy. And what we lean on very heavily is the bottom line there. It's self-repair and self-redundancy. You have to assume that parts are going to be bad and plan for repair parts and repair elements in those. I'm going to give you an example, and memory is a really easy thing because it's kind of inherently done for repair. This was a part that was Tezeron Semiconductor, which is a predecessor company to Enhance, did. So we had a stack of 16 layers of DRAM, then a controller layer and an IO layer. So there's probably were about 100 million total interconnects vertically in this, and it had on the order of 1 trillion devices in the stack. So it's not too surprising. We don't test the DRAMs beforehand. They have to yield in place, and we needed strategies to work with that. Well, by planning differently, as we added DRAM layers, our yield did not go down, it went up. And the reason it went up is we shared repair and redundancy vertically in the stack. When you do it laterally, it's hard to share repair bits on this side of the die for a bad memory array over here. Get in the picture, over here to over here. But if we do it vertically, those layers are very close together. They're on the order of about, in this case, they were about 14 microns apart. So we could share redundant rows and redundant columns vertically in the stack. So unless you had a systematic problem in your design that caused failures always in the same area or something in the processing, if they're normally randomly distributed, you actually get more repairability in by stacking than you do in 2D. So you can get better yield in a 3D device than you can get in a 2D device. The moral of the story is you think differently. When you move into these areas of very advanced packaging, and especially 3D, it requires a shift in how you think about how you make parts yield. Other obvious, extensions of this are spare processors. We all know that, you buy a 4-core processor, it probably really was 8 cores and there was a bad core, or you buy an 8 and it was really a 12, or a 12 was really a 16. The processor guys have been doing this for a decade already. There's things like smart interposers that can be done to reroute around bad things. We've looked at doing FPGA repair kits. What many of you may not be familiar with is when we do a 7-nanometer chip today, you put in unused, uncommitted, spare logic into those devices. Now, it's not an FPGA in those devices, but you put in all the transistors, so you can come back and make a couple of metal mask changes and spend only, $1 million rerunning the part rather than, 15 million with a new mask set. So it's very common to use repair kits today in advanced semiconductors to come back and fix logic flaws. An extension of this is to use, FPGA-based repair kits that are built into 3D devices. Another thing that probably most people don't know is HBM memories have redundant I/O. In the first generation, they used the parity line that could be taken over and used for a data line if it failed. In the later generations, they have dedicated redundant I/O because for them, that was the Achilles heel in assembly. As you stack things in HBM, they use TSVs, but they use solder balls in between them. Planarity is an issue. The stack goes through multiple thermal cycles as it's assembled sequentially, as well as onto the interposer, and then eventually onto a substrate. You have to be able to go back and repair those devices. In fact, HBM memories are repaired, fuse repaired for bad, rows, columns after the package assembly is done with the GPU. Some data points. Looking down the road, it seems to be that the market is deciding that chiplets are a likely direction to go. There's very little benefit to building analog circuitry at 7 nanometer. And in fact, 7 nanometer analog is gargantuan. You have to tune virtually every transistor because transistor matching is abysmal. There's really no reason to do it. So if you look at a typical cell phone chip, there is enormous cost benefit to you build a lot of that analog at 65, 45, maybe 28 nanometer, and you leave it there. It improves time cycles because now your new 7 nanometer or 5 nanometer design is really going to concentrate on the core digital circuitry, which really is what changes generation to generation. A very important thing, known good die is really known not bad. It is illusory to believe that a known good die is actually fully tested. Even if they do a really good job of testing it, it is not going to be done at speed. So you need to be aware of it. As I mentioned earlier, 2.5 3D have lots of I/O. Die probing is very difficult. Die probing actually can cause more damage and reduce yield more than just simply doing blind assembly. I'm going to go into the process here, and I don't know how I'm doing on time, but I have about 7-8 more slides here. So this is the DBI process. It's the direct bonded interconnect. We do this at wafer scale. We can also do it as die to wafer. You start with a wafer out of the fab. We have a metal bond pad pattern at the top. Usually that is done in copper. It can also be nickel. Under CMP, we polish the surface atomically smooth to typically about 0.3 nanometers RMS. The wafers need to be very planar. They also need to be pretty flat so that they bond well. We do a plasma activation. And what that does is it takes the silicon dioxide, or it could be silicon nitride, and it opens up the bonds. And we end up with silicon with, instead of oxygen hanging on it, you have actually of the oxygen, but instead of attached to the silicon, you have hydrogen hanging on it, or nitrogen hanging on the tips. When you bring two wafers together at room temperature, it will spontaneously bond. There's a van der Waals bond that's formed immediately. I didn't put the film in today to show it, but it's in real time. You can actually see the bond wave propagate if it's a glass wafer on the top, and you can see it move. After that, we anneal it, and once the annealing is done, it's permanent. We actually do a check to make sure that the alignment was good before we do the anneal. And if the alignment wasn't good, we can take the wafers apart and do a touch polish, we call it, to clean up the surface, reactivate it, and bond them again. How this works is after we've done that room temperature bond, it kind of looks like on the left-hand side. The metal we polish so it's recessed 30 to 50 angstroms from the surface. When we heat it up, we use nature, physics here. Metal expands more than the oxide. The oxide acts to pull this together. The metal extrudes, and it does grain growth across that boundary. So after we're done, typically this bond interface is stronger than the interfaces at the lower layers of metal on either wafer that's bonded. Here's some pictures of interconnect that we've done. Most of what we do is 3 to 5 micron pitch. And as I mentioned earlier, the smallest pitch we've done to date is 0.8 micron. Here are some CSAMs, which are scanning acoustic microscopes of what the bond interface looks like. The lines in X and Y that you kind of see, those are actually the edges, the boundaries of the chip. You're seeing the scribe lane areas, which reflect the acoustic energy a little different. And what a bond defect looks like, if you go to the left-hand photo down near the notch, you see a little white kind of half moon near that notch. That's actually a bond defect. We can do very high stacks. On the right-hand side there, you see an 8-layer stack. The TSVs, which are the little vertical lines, those are a micron in diameter and about 6 microns long. Those layers are, I think these are about 12 microns or so, probably 14. This is 80 layers of metal plus the bond pad, which is at the very top and kind of right above where it says TSV8. That's a metal, an aluminum metal pad that's making contact to the via, which is to the right of that. We actually have a production part that has 16 layers that we assemble. And I have some disappeared pictures here, unfortunately, that show gallium arsenide wafers. The good news is the one on the right is actually what it looks like up close, indium phosphide. You can do heterogeneous bonding. We do gallium arsenide, silicon carbide, lithium niobate, gallium and tinamide, gallium nitride, all in various combinations and with CMOS. So you can get very, very high figures of merit. If you're familiar with Johnson figures of merit, we can easily get 3 orders of magnitude performance improvement as opposed to any silicon process or any other single process. Heterogeneous integration gives you a lot of performance boost. And I don't know why it's doing this to me. I'll tell you what, just in case this happened, I did prepare a very quick backup to a PDF. And that doesn't want to show either. Like you guys were saying earlier, if anything can go wrong, it does. Okay, we'll go back just to the PowerPoint here. I'm almost done anyways. So I'll move on. Other things that we can do. The previous slide, by the way, was just showing off some of the die to wafer work. Looks very similar, except it's die sitting on other die. We also do quilt packaging. This is an interconnect technology where we form pins on the side of the die. And you can abut these. It allows you to, basically like Lego blocks, put things together. You can also build these three-dimensional devices. We are currently working on a DARPA program with a few other companies. This technology, by the way, was developed by Indiana Integrated Circuits. It's their technology. We have brought it into our fab, but we're building an IR sensor that's about the size of half of a golf ball with it. And we also do microtransfer printing, which allows us to take literally individual transistors and pick them up using an elastomer and move them to a die. This is, it's being used to build LED displays on large format panels. Acceloprint developed this technology, and that's the direction they actually split the company and are commercially exploiting that. We've been interested in this for putting down gallium nitride power transistors for RF and power converters on top of silicon devices or other 3-5 materials. So you can put down chips as small as perhaps 25 by 25 microns and directly interconnect them on the surface of another die. You're really transfer printing a very thin layer on the order of about 10 to 15 microns of material containing that device to the new host layer underneath. So in summary, what Enhanced does is, you know, we're a small, medium scale semiconductor manufacturer. We have a fab in North Carolina. I nominally talk about us as being a back end of line fab. We don't build transistors. We do a lot of unique things. We do build diodes. So the wafer at the top there is actually a dark matter detector. It's a 5 millimeter thick silicon wafer that we build. So we do a lot of this very novel processing, primarily for mil-aeroscience, medical markets, and a lot of other custom sensor markets in the industrial area. And with that, I'm done, and I'm open for questions.
Hi, Robert. Thank you very much. It was a great presentation. Couple of questions. One that came through on, you mentioned of double patterning and the move to EUV. Is the reference to double patterning here a side-to-side stitching, or in order to exceed ASML reticle size for a larger die, i.e. greater than 25 by 31?
The double patterning is actually to produce things below the resolution limit of a stepper. Using immersion 193 technology, you can print at about 40 nanometer line in space. So, but you can actually align the mask to about 4 microns. So, or 4 nanometers rather. So what you do is you do one shot that has every other line, and then you change out the mask and you do another shot that has the intervening lines. And you can then get the equivalent of 40 nanometer pitch out of something that started with 40 nanometer resolution. Field stitching is something that's commonly done to make something bigger than the reticles. Today's reticles, most of them are 26 by 33. So if you wanted to build, you know, an interposer that was 50 by 50, you'd have to tile 4 fields. Field stitching works very well. You have misalignment at the edge, and that's typically on the order of nanometers to small tens of nanometers. It depends on the stepper. But the cost impact of double patterning is that you had to go back to use that immersion scanner twice to print those smaller details. That was the point.
Gotcha. Alrighty. Couple of questions that I had. One, obviously in 2.5D and 3D assembly stack ups and all that. I guess, where do you see the biggest challenges for the assembly subcons or dealing with that type of stack up technology? I know, reliability is probably a concern. You talked about interposers and CT mismatches going on. I guess, where do you see it in terms of assembly or reliability, the biggest challenges?
I'll start with reliability. In most of the cases that we've seen, the reliability stems from temperature excursions, temperature cycling. It's the CT mismatches between all the materials, and it doesn't matter whether you're using the hybrid bonding, as I've talked about, or you're just doing, micro bumps. It's when we drive something to failure, we're doing it by temperature cycling. I can tell you that the hybrid bonding, the DBI, is actually very tolerant. We have more than 100,000 device cycles from -65 to +150 with 15-minute dwells, and it survives. And we've done that on hundreds of devices. So it's very robust. We guarantee it to be good for 1,000 cycles in that range. It's better than the solder bumping. The other real challenge is planarity. And this is the problem in HBM today, and why we don't have taller stacks. To make taller stacks, the height of the HBM gets higher than the processors in the package. It's a package height limitation, so they have to make the die thinner. As you make die thinner, they distort. You end up with a lot of curvature, potato chip effects. Then you put all these little tiny solder balls on it, and the problem is not all the balls can touch the wafer below or the die below because of the shapes. So they've been stuck at about 8 layers of DRAM on a controller in the envelope, and I'm pretty sure it's been announced. Hynix is using hybrid bonding now, and they've said that they're going to be able to make 16-layer memory stacks available at some future point because of the DBI process technology. When you bond it together, because of that van der Waals force pulling things flat, it flattens the die. So those are the two biggest things. I think beyond that, the real challenge for a lot of the typical OSATs is these require a lot of semiconductor technologies. And you go to an OSAT and you start talking about piece of equipment that costs millions or tens of millions, and they faint dead away on the floor. They build whole manufacturing lines for $30 million. They're not used to buying pieces of equipment that cost $30 million.
Right, understood. Are you seeing any major drops in, we'll call it, assembly yields? Obviously, typically everyone tries to target high 90s as well as possible, but as the technology is growing, I would assume the yields are dropping down.
Well, there's just a plain truth that as we add more and more transistors in assembly, we build things with part per billion yields. Well, that's great, except that we're building things with trillions of devices now. So we're destined to fail. The DRAMs are the poster child. I have a friend at Micron, and he liked to say, if you were getting prime die at the end of the line, and prime die are die that work without repair, you're just not trying hard enough. It's a tacit assumption that repair and redundancy is just required to build state-of-the-art memories as well as state-of-the-art processors. And I think even in FPGAs or even our cell phone cameras, every cell phone camera has bad pixels. All of us staring at our displays, well, we all know that there's a high likelihood that there's 1 or 2 pixels on the display that are really defective. We just don't see them. We need to change to a methodology that is accepting of defects, or defects are repairable in it. And as we move to chiplets, one of the things that didn't show up on my slides, unfortunately, I have an interposer where we have 17 different die on it. The probability of having 17 perfect known good die on an assembly is slim none in a negative number, or at least really close to that. So, you know, you incorporate into all of those schemes compensation for bad I/O. I participate in a lot of the test conferences, and I'm a strong believer that what we're going to end up with is devices that test themselves, a unified test format, probably through JTAG, that says, go test yourself, do you work? It's the responsibility of that chip to report back, yes, I'm good, I've tested myself from pin to pin, and I'm passing. And that is how we're going to determine known good die moving forward and isolate things in the assembly, as well as be able to incorporate repair and redundancy into those assemblies.
Great. Another question, sensor going off here. Anyways, another question that came through, what market applications would require testing to -60 other than mil-aero in very far northern geographies?
Part of the reason that we go to those very low temperatures is not so much that they're going to use them there, but are there any issues in creep that, you know, it's an accumulated problem. We want to make sure that we have a really wide safety margin in the reliability of our 3D assemblies. So most of our customers, let me see how I can do this. About 70% of our customers are mil-aero, and they like having parts that are like -55 to +150, or at least +125. We do have parts on orbit, and they prefer even extended ranges. I will also annotate, we do have parts that run at cryo. We've done IR sensors that run at 77K. We've built some parts for quantum computing that run in millikelvin. So I have parts that undergo excursions on the order of 300 degrees repetitively, 300-400 degrees. So we did that really to prove out the robustness of the assembly.
Gotcha. Ready. Not seeing any other questions come through on the chat box. Thank you again, Robert. Great presentation.
Certainly, and I will send you a copy of the PDF that, if anyone wants, they can have, and that does have all the pictures in it, and as well as my my phone number and email on the front slide.
Great. Thank you so much. Pass it back over to you, Richard.
Okay. All right, thank you, Robert. Excellent presentation. So our next presentation will be a bit of a tag team between Hua Xia and Dave Dwyer from Hermetic Solutions Group. Oh, I want to make sure I can be heard.
We can hear you, Richard.
Oh, good. All right. So Dr. Xia is the chief scientist at Hermetic Solutions Group. He received master's and PhD in condensed matter physics from Nanjing University. I think we need the slide for the next speaker.
Yeah,
okay, you're showing the previous speaker.
Yeah, I can't share until you allow me to.
Oh.
Yeah, sorry, it seems to have locked up again. I don't know why it does this.
All right, well, I'll just talk through it then.
Right, sorry.
Prior to Hermetic Solutions Group, Dr. Xia has been technical leader at GE Global Research Center and chief scientific advisor for Halliburton, and has maintained an affiliation with the College of Nanoscale Science and Engineering at Albany, New York. He's credited with 120 US and international patents, received the GE Gold Medallion Award and the 25th Patent Award in 2012. Dave DeWire is Vice President of Global Business Development for Hermetic Solutions Group. He's has a strong background in ceramic, metal matrix, composite, and various thermal management materials, has led development of packaging for gallium nitride, gallium arsenide, silicon carbide, and LD-MOS devices. He's been awarded 4 US patents related to modular low-stress packaging materials. I understand our 2 speakers are going to break up the presentation between the 2 of them. So I will give it over to you, Dr. Xia and Dave.
All right. Okay, can everybody see that screen?
Yes, we can.
All right, good. All right, well, before we start, I want to thank everybody for attending this presentation on uptake capacity of hydrogen getters. And certainly want to say that it's great to be back in New England. I'm from New England, live in Colorado now, so I guess I can say that I'm there virtually. So anyway, before we get started, I do want to say thank you very much to my colleague, Wah. Without Wah's contribution, this presentation wouldn't have quite the flavor that it does if it were left up to me. So just a quick overview of what we're going to talk about today is certainly I'm going to do a little bit of a commercial on Hermetic Solutions Group. I'm going to talk about the importance of gettering technology in package chains and the effect of particularly in this case of hydrogen and how it affects failures in electronic packaging. And we'll talk a little bit about the kinds of severity that you can see or we can witness in with the presence of hydrogen in hermetic packaging. I'm going to talk a little bit about a solution for managing hydrogen and in some sense moisture in hermetic packages, and talk a little bit about some of the technology that goes behind behind our testing and validation of this solution. So here's the commercial. I promise I won't spend a lot of time on it. Hermetic Solutions Group, we're kind of a new company in terms of the name of Hermetic Solutions Group. Rather, the companies that make up Hermetic Solutions Group are legacy companies that have been around in some cases back to the 1940s. We are made up of companies like Sinclair Manufacturing in Norwood, Massachusetts, Lightron, which is a laser manufacturer up in Agawam, Massachusetts, Pacific Aerospace out in on the West Coast, and the Hi-Rel Group. Many of you probably are aware of Hi-Rel products, Hi-Rel alloys, and Hi-Rel lids. They've been around probably for the past 30 or so years. So all of those businesses make up Hermetic Solutions Group. I do want to shout out to Robert. We do have a location out here in Sequim, Washington that probably uses a lot of your blasting cap product. We manufacture explosively clad materials at that facility in Sequim. But just quick overview of us, we're about 900 employees and about 80%, 75 to 80% of our business now is in the mil aero defense market. But we do also play in the power and energy, telecom, and optical and medical businesses as well. So we're kind of a global company with 10 rooftops. And we have multiple certifications at all of our manufacturing facilities. And their end of the story on Hermetic Solutions Group. So let's talk a little bit about the importance of gettering in the value chain. Every type of electronic package, particularly in our focus in the hermetic space, has a concern about free gases within the hermetic enclosure, gases and moistures that could affect performance and reliability of that package architecture over the long haul. And these packages are, there's just some pictures here that kind of give you an idea of where these gettering technologies can play. Most integrated microelectronic packages and devices outgas hydrogen and moisture and carbon dioxide just naturally as a state of the manufacture of the package. And that presence of hydrogen, which we're going to speak about today, inside that electronic package can degrade those packages over time by forming hydrides. And those hydrides in that space can either affect the wire bonds, the solder, all the solder connections within the package, and also affect the gates themselves within the semiconductor structure. So today, we're going to talk about getters being used to remove hydrogen, and then its resultant effect on the reduction of moisture in the package in all these hermetic packages. So HSG and a lot of other manufacturers make all kinds of gettering technologies. The picture that you see here shows you different types of getters, how they're applied, and the what those typical materials may scavenge within that hermetic enclosure. A lot of these products are either silicon based, or some are zeolite based as well. Today, though, we're going to talk about, like I said, specifically those getters that scavenge hydrogen, and in this case, particularly this palladium kind of architecture that you see here in the lower image. So what causes this hydrogen-based device failure? As I said earlier, it typically affects the long-term reliability if it's in high enough concentrations of the microwave module or the microelectronic package by attacking the gate materials themselves within the semiconductor structure. Also, when hydrogen is present within a package that has oxygen in it as well, they can very often combine and create moisture within that hermetic enclosure. So we use getters to capture those contaminants and the volatiles within inside that enclosure, and essentially scavenge that material and hold it in place so it can't act freely within that hermetic environment. This is a great schematic that really kind of shows the failure severity when you combine outgassed hydrogen with outgassed moisture, and it's very intuitive in the sense that as hydrogen levels increase within the hermetic enclosure, you start to get into severe failure modes just by the act of the hydrogen in the enclosure, that hydrogen attacking those gates within the semiconductor structure. And at the same time as oxygen or moisture are elevated within that enclosure, you also start to reach this severe failure mode. Now, in the combination of the two, you get up into this space where you have high levels of moisture and high levels of hydrogen. That's really a challenge for most device technologies, and typically spells failure. So when you manufacture, in this case, we're going to talk about palladium and the use of palladium. Excuse me. In our case, we're taking pure palladium foils, and we're building these large reels of palladium foil, rolling them down, compacting them into different thicknesses that I'll talk a little bit about later. But building this material to varying thicknesses to fit certain headspace within a hermetic enclosure. So as the material is rolled, we will then process it into any kind of custom shape so that this material can then be included into the hermetic package. So typically, as this material is rolled, we can build this material, as I said, in pretty much any thickness, any kind of form factor, length, width, and thickness, and build this material as thin as 2/1000 in thickness, all the way up to whatever you'd like, whatever the headspace in the package will allow. And then we can custom build this material to pretty much any form factor to fit in the hermetic space. Typical attachment methods of this material are either epoxy or tack welding of the material into the hermetic enclosure. And why do we use palladium? In this case, palladium itself has a very high absorption capacity. Here in this example, palladium has a capacity of 11.2 torr liters per cubic centimeter. And that's really quite high as compared to any other kind of native metals. And the absorption rate of this is around 0.5 to 40 ppm per minute. Again, very rapid absorption rates. The other nice thing about palladium is it does not require any kind of thermal activation as compared to some of the other zeolite type or silicon type materials that are commonly used. So why do we, what's really great about palladium? I really love this chart in that it shows the working regions of the absorption capacity of palladium. And you can see in this graphic image that we have a temperature range in degrees C here, and compared to a desorption rate on this part of the chart. You can see that the material, that this palladium can absorb hydrogen in the region 1 up to about 320 degrees centigrade. Very high, higher than most hermetic packages would be used. Typical working range of most hermetic packages today is up to about 150 degrees C. So the material shows great absorption capacity up to about 320, and then the material becomes ineffective within this range of 320 to roughly 460 degrees C, and then at those higher elevated temperatures starts to absorb hydrogen again. So, this is a great image to show the effectiveness of this material over a really broad temperature range. So to test this material, my colleague Hua developed this test process with our friends at Oneida Research. And in this case, we're doing a manometry measured absorption of this this hydrogen getter, essentially a palladium substrate that's placed in a sample chamber. And in this test, we introduce a known value of hydrogen into the sample chamber. In this case, we were using a 3% hydrogen within the gas that's introduced into the chamber, and about 97% argon in this case. So we subjected the sample of palladium in the sample chamber to this gas mixture, and we decided to look at take away a gas sample after so many hours of operation. And in this case, this sample, by the way, it's about a 1-inch square, I think, of material was placed in the chamber. And at 300 minutes, we withdrew a sample of the gas in this chamber and did an IBA analysis of that gas sample. And we see that what was 30,000 ppmv of hydrogen, that sample now shows that the getter has absorbed and reduced the hydrogen limit down to 25,563 ppmv. So then we took that very same sample and ran it up in this case. I'm sorry, I jumped a slide. So if you take this, if you evaluate this 300-minute sample, it's essentially saying that after 300 minutes, this sample absorbed 4,437 ppmv over that 300-minute space of time. So then we continued to run this getter sample up to 4,000 minutes. And you can see here on the left in the IBA analysis that the level of hydrogen has continued to drop within the sample, the gas sample that we pulled. And essentially over that 4,000 minutes, we've consumed roughly a little more than half of the hydrogen that was available in that sample. So it shows that kind of a curve of continued absorption of hydrogen. So how does this material absorb hydrogen? And I can certainly call on Hua here to speak a little bit more to this, because I'm not quite as aware of the chemistries as Hua is in the effectiveness of uptake with argon present.
Okay, this is a model we try to use to explain what's really absorption capacity from this palladium getter. So we know that the testing uses mixing the gas, the argon hydrogen. So we developed a model to say, hey, this is a kind of mixing gas, and how we can predict what's the absorption function, and also what's the gas absorption rate. We can predict it. So we know that there are many theory behind talking about the material outgassing kineticals. This is we use a reference to that kind of theoretical work we developed here for the mixing gas kind of a prediction. What's really absorption concentration as a function of time, and also what's the gas absorption rate as a function of time. This is we can see there's a index called mu, is very critical used for the outgassing formula. And normally for hydrogen is 0.5, but in our case, we're talking palladium absorption rate. This is the mu we found is about 0.55. It's a little bit different. But this is reflect the multi-gas absorption. It's not outgassing. So that's a little small difference. But this is give us a basis to understand how this is the palladium as a gator and how we can predict this is the palladium as a gator at a different kind of capacity and absorption rate. And that can guide us to use it for different package application. So next slides. This is the slides give you, both testing data and also theoretical. This is the kind of a modeling fitting. And then the data on the top, we say the pressure, PT0 minus PT is the measurement data from the RGI testing, because in the testing chamber, you only can test it, the pressure, partial pressure variation. Use that kind of a variation, we can calculate how much hydrogen in ppm absorbed as a function of time. And in the bottom black color data is the absorption rate. That's only say the concentration change as a function time. You can plot as the data is in black color. Use our formula and you can predict it and or fit this data. You will find that this mu factor only about 0.55, and both the simulation from the absorption rate and also capacity is pretty good predicting what's the hydrogen absorbed by gator. That's the from delta T, you can see 4,419 ppm, and IVA tested, and it's a 4,437 ppm. That's the small difference, but we don't see that kind of big, kind of very consistent, which this is a theoretical modeling. Typically, we can see the absorption rate. Sometimes we very concerned. If gator absorbed the hydrogen very slow, the device may be damaged already. So we would like this gator can absorb the hydrogen as fast as possible, but how fast is fast? In this case, we can say at 300 minutes, we still have about 10 ppm per minute kind of a rate. But I try to remind everybody, normally a packaging material outgassing rate is about 0.1, 0.2 ppm per hour. So in our case, this gator can be 2 or 3 orders faster than any material, packaging material used in the electronic package. Okay. Dave, you want to talk about this?
No, go ahead while you finish this one.
Okay, this is the kind of the data we finally make this gator, 1 inch by 1 inch and a very, very thickness, because this can give us a guideline how much hydrogen we can absorb from a package. A lot of time depends on the volume of the package. The total outgassed hydrogen could be 1% or could it be 2%. We normally define below 5,000 ppm is low outgassing package. If you 1%, 2% hydrogen in total lifetime, we normally say 10 to 20 years the package, lifetime. We have to calculate. If we say, hey, we have over 2% maximum hydrogen outgassing from this package during whole life, the gator we have to select it is really have more than that kind of 2% capacity. So this is the give one kind of a guideline how this palladium material can be as a gator at a different thickness. 2 mils, 4 mils, 6 mil, 10 mil, 15 mils. Each thickness reflects a different kind of capacity. You know, for example, 6 mil, the maximum absorption is 95, 100 ppm, look at 95 cc. If we say, hey, we have a package, it's a kind of a 10% hydrogen, could be in 20 years lifetime. So it's somehow we can close to select this kind of a getter inside the electronic package to mitigate any potential failure, you know, due to the hydrogen outgassing cause trouble. So this diagram also can give you understanding when a getter approaches the kind of maximum absorption capacity, the absorption rate will be slowed down. So how much slowdown is acceptable? In our case, we can talking, for example, 15 mils kind of getter that's really can absorb 237,000 kind of ppm. This is in real life, it may be very, very rare cases. But even though in these cases, this getter, if absorbed close to saturate, they still have a 0.5 ppm per minute kind of rate. I think that could be a very good. We do have other publication and regarding what's the material outgassing rate, what's from a different material like epoxy and a polymer metal. That's when we can say, hey, this getter can provide a factor of 2 or 3 faster than any outgassing material. That's ensure the reliability of the electronic package. Okay.
That's good, Bob.
You go ahead.
Okay. So one of the things that we wanted to look at was we wanted to try to evaluate what level of uncertainty the testing would provide us in RGA. And through some of these calculations, using different getter thicknesses, different mass levels of palladium and thicknesses, we're able to determine that the level of uncertainty in that RGA sample is around 186 parts per million. So then we wanted to look at this in a practical sense, you know, using this palladium foil in a hermetic enclosure. So in this case, we designed some packages. The dimensions are shown here. These are roughly about a 1-inch square package made out of aluminum, where we have introduced a getter, this hydrogen getter in some of these enclosures, and in others we built some control samples. In the tests that we performed here, we wanted to use the harshest conditions that we could use in these hermetic enclosures. So we installed the getter on the inside of a plated lid using epoxy, and before curing the epoxy, we welded these packages together. We did not perform a pre-bake of any of these packages prior to this test. After they were sealed, that's when we baked these parts out. The intention here to drive as much volatile out of the plating chemistries and the packages themselves, the epoxy systems, et cetera, drive as much volatile into this enclosure as we could. And this is an example of some of the some of the parts that were tested, and in this case, you can see that the hydrogen levels of these tests were down as low as 130 ppmv, 116 ppmv, 115 ppmv, and far below the level of uncertainty that we've evaluated originally, looking at the performance of this material in RGA. So it's very effective as a getter for hydrogen in this case. So then when we looked at these samples overall, took a look at the control samples, because we did include control samples within the grouping, you can see in this case that after this process, we were, the parts with the getter showed very effective and really dramatic reductions of hydrogen within the enclosure, wherein the control samples all had levels of around 1400 and 1600 ppmv. So very effective, shows that it's a very effective scavenger of hydrogen. So in summary, everybody should understand that the package constituents, everything that makes up a hermetic enclosure, can outgas harmful species of gases inside that enclosure. The very metals that make up the package, the plating chemistries are known to outgas hydrogen, and organic materials like epoxies and things like that. And that these harmful species can create additional harmful byproducts when combined, for example, with oxygen. That free hydrogen combined with oxygen creates moisture. We understand palladium is a suitable material for the use of getting hydrogen, and that it will affect the reduction of the formation of moisture. The neat thing about palladium is that not in all cases are you able to do this, but palladium can be tack welded to the inside of a package, eliminating the use of epoxies or other materials to hold it in place. So you eliminate kind of one level of materials that can outgas volatiles into the package. The other neat thing about palladium is you can roll mill this material to varying thicknesses. It can be stamped into different sizes and form factors to fit in, very low headspace areas. And lastly, palladium does not require any activation. Before we go, I want to give a shout out to our veterans and active duty personnel, all police and firefighters, and frontline healthcare workers. Thanks for your service. And lastly, here's our contact information for both Wah and myself. Please feel free to, if we don't have time today, to reach out to Wah and I. We'd be happy to help you with any additional questions you may have. And with that said, we'll take any questions from the group.
Thank you, Dave. Thank you, Wah. Great presentation. Question actually that I have, I know you talked about various thicknesses. It can be stamped in various sizes. Do you have guidelines for potential designers, packaging engineers on what that size should be based upon the volume in the package or the assembly materials that are being used, whether it's epoxies to down substrates or dye, such? And do you base some of your sizes off of not only the volume in the package, but also the materials that are being used?
Yes, this is Hua. Yes, we do. We have the guideline actually based on the package volume, package material, and also package operation temperature. That's three factors. And that gives us, we normally say we need a safety factor, and based on a gator, how a safety factor now this gator can work in a specific package. So that's the reason we develop a kind of other the safety factor based kind of metrics to decide what gator it is supposed for anybody's application. But we do have one white paper, circulated outside to talking. This is how you can select a gator for your application.
Alrighty. Another question that came in: would the thickness of the palladium material make a difference in terms of hydrogen absorption / desorption in terms of getter working temperature range?
Why do you want to handle that?
I'm sorry, I didn't fully understand what's the question.
The question was, would the thickness of the palladium material make a difference in terms of hydrogen absorption / desorption in terms of getter working temperature range?
No, the answer is no. It doesn't depend on the thickness.
Okay. Not seeing any other questions that came through on the chat box. Again, thank you, Dave and Wah. Great presentation. Definitely appreciated. I guess we'll pass it back over to you, Richard.
Thank you, Mike.
Yeah, thanks for having us.
Dave, thanks. You need to stop screen sharing.
Yeah, there you go.
Thank you.
I think, Richard, you're on mute.
Richard, you appear to be muted.
All right.
I don't know if you want to pick up, Dave. I know Richard wanted to talk about the May.
Right. Okay. Well, all right. Let's carry forth. Richard, if you can hear us, you do appear to still be muted. This is the fourth technical session that we extracted from what we had intended would be the 2020 in-person presentation in May of last year. We will have additional technical events coming up for the chapter. We have both a website and a newsletter. And if you are in the mailing list for the New England chapter, you will receive the emails that go out as advance notice for each of those sessions that are coming up. And thank you very much to our speakers today. We have an upcoming chapter technical meeting, May 19 at 5 p.m. is the schedule. Rajiv Iyer will be the presenter from Binghamton University. His topic will be process development and sustainability of fine volume adhesive jetting in microelectronics applications. Again, that would be May 19 at 5 p.m. in the evening. Richard, looks like you're not on mute now. Do you have any additional comments on this presentation?
No, I would like to thank both of our, all three of our speakers. Those were very interesting and informative presentations, and we really appreciate the effort that they made to share them with us.
Great, great. Fully agree.
David?
The fact that...
Dave?
Yes.
Not to take any time, I would like to just add Rajiv's current affiliation, more related to his talk, is at Medtronics.
Oh, yes, that's correct. Yeah. Okay, I went with what Matt had sent this morning. That's correct.
Yeah, Binghamton is his university.
Yeah.
But the work, I believe the work he's planning to present is based on his activity at Medtronic.
Yep, thank you. And most everyone who is on this session today obviously is here and knows that we have a website, but the website is, just to say, imapsne.org. And that concludes what we have for today's session. Thank you, Richard. Thanks, Matt.
Thanks, everybody. Excellent session.
Thanks, everybody.
Thank you.